Okay, so welcome back. Today we're going to start a new series where we're going to be talking about what you see here. And this is a motherboard from a laptop computer. And the goal of the series is to explain how these things work. And hopefully we're going to make it very simple for you to understand what the different components are, what the different circuits are that work together with a laptop to power it and to power all the different components. And we're also going to be doing some simulations of some of the circuits in what's called LT Spice, which is a free electrical simulation software. I did a 12-part series on that. I encourage you to look at that. A great way to understand how these different circuits work is to simulate them. So we're going to talk about the different component circuits, and we're also going to talk about some ways that you can use to better learn how these things work. You know, it's one thing to watch a video on YouTube, but it's another thing to actually get the components and understand how to get resources, to understand what the different chips are, what the integrated circuits are. So there's a lot to it that will help you to figure all that stuff out. So now let's first focus on what is arguably the most important part of your laptop, and that is the power system that supplies power to the motherboard and other components of your computer. Now, why do we want to focus on the power system? Well, as I said, arguably it's the most important part, and there's a couple reasons why it can be considered the most important part. First of all, if you look at your motherboard, there's a lot of components, very complicated components here, like the CPU, the GPU, these very complicated integrated circuits that you can't really do much with. I mean, you may be able to replace them, probably not. But the power system, a lot of these components are related to generating the correct power to supply the motherboard and the other components. And those are much easier to access for anybody who wants to work on it. So accessibility is one reason why it's important. But the more important reason is that, as you can see here, we've got a motherboard and we've got two sources of power. We've got a battery that can supply the motherboard. Also, we've got this wall adapter. And what the wall adapter does is it takes the voltage from the power company. Here in the US, it's 120 volt AC RMS sine wave, like you see here. And it converts that high voltage sine wave into a DC voltage that is generally around 19 volts DC, a little bit over, and it feeds that into your motherboard, which then feeds all of the components of your laptop. Now, the problem with this compared to a battery, by using a source of voltage coming from either the utility or an adapter chosen by the user, there's a lot of room for catastrophic events to happen. So for example, if I have voltage coming from the wall outlet from the utility, they could suddenly have a very big spike in voltage that's unexpected, and it could get through this adapter into your motherboard and cause some damage, especially if the user uses a piece of junk adapter that has no protective components to make sure that doesn't happen. So any external components and external sources of voltage leave you open to some significant damage if the user isn't taking care of his adapter and if the utility has an unexpected, lightning storm or whatever. So this is kind of a dangerous thing that you really need to protect against. And as we'll see in a lot of the design of these motherboards and the power components, there's a lot of protective circuitry designed to do just that, to make sure things don't blow up, and if something bad does happen, to make sure it doesn't cascade and get worse. So that's why we're going to focus on this input power source that takes voltage from the wall outlet, converts it to DC, supplies the motherboard and all the other components of the laptop, and also charges the battery. So if we plug 19 volts from our wall adapter into that DC input jack, what does it do? Well, basically it has to power all of the laptop components. The CPU, the GPU, the RAM, any onboard storage like an SSD, cooling fans, the keyboard, any Wi-Fi cards, and the display. Of course, the laptop LED or LCD display, you need voltage for that. And as I mentioned, every single integrated circuit on that board requires power in order to function, to do all its logical operations. So all of these components need to be powered by that DC input volts. Also, we have a battery, don't forget, so we're going to have to take that DC input volts of 19 volts and somehow figure out how to charge the battery. Also, we're going to have to power any external devices. For example, if we have a USB thumb drive connected to one of the USB ports, you got to power that. Any Ethernet. So all of these things have to be powered by this DC input volts. And somehow our computer circuitry is going to have to figure out how to do all of that. And keep in mind, these components can't generally operate on 19 volts. You've got all of these different components that require different voltages to operate on. So you can start to see that we have a very difficult task taking this 19 volts, bringing it into the computer, making sure we're protecting against any very bad situations that happen, high voltages or high currents or short circuits, and also figuring out how to convert that 19 volts into generally lower voltages required by all of these components. So for example, a typical CPU might require voltage in the 1 to 2 volt range. A GPU might require 0.5 to 2 volts. Your RAM, depending on the age, might be 1.2 to 1.5 volts. USB is generally 5 volts. Ethernet is generally 3.3, and SSD might be 5 volts and 3.3. Your fan could be 12 volts, 5 volts. Your LED display could be 12 volts, 5 volts, 3 volts. The battery is generally around 12 volts. So you can start to see we got a lot of circuitry in the power system of your laptop that's going to have to convert that 19 volts down to the required voltages for all of these different components. And if you look on the motherboard, if you get familiar with your motherboard, you can start to recognize, hey, here's some power circuitry for one of those, and here's power circuitry for another. And a lot of these big components are basically just there to convert that 19 volts to the power required by each of those components. So again, we have our motherboard, we've got our AC input adapter, and now we are going to look at how we can start to take that 19 volts and implement those things that we talked about before, protective measures and also measures to make sure that we have good voltage so we can start everything up and also so we can charge our battery. So let's first think about what we need to do for the very basics of power management with your laptop, and it's called power management. So the first thing is, okay, say you've got your laptop and you want to turn it on. Well, to turn it on, the user will generally go to the power button and press it for a short amount of time, and that should turn it on. Well, the logic that's used is a little bit more complicated. If the user presses the button and the computer senses that the DC coming in from the input jack, that 19 volts is there, or it has a source of voltage from the battery, and there's no short circuit sensed on that 19 volts, then it will turn it on. So what seems like a very simple button press is actually requires a lot of logic in our computer to make sure that all of these conditions are met so that we actually can turn it on and not have any problems. So we've got some logic here. If the button is pressed, if we sense good voltage from either the input jack or 12 volts, and if there's no short circuit sensed on our main rail. And there's also other logical requirements that you can use to check before you actually turn this on. But we'll use these as a very simple list. Now, keep in mind, in order to do this, we're going to have to measure these things so that we can have a integrated circuit that can use those as input and do some logic and say, okay, I meet this condition, I meet this condition, and I meet this condition, therefore I'll turn it on. So we're going to have to measure somehow if the power button is pressed by the user. So we're going to have some signal into our power management circuit that says, yes, the user pressed the button. And we're going to have to measure if there is actually 19 volts at the DC input jack, or there's 12 volts at the battery. And we're going to have to somehow sense that there's no overcurrent or short circuit on our main power rail So we're going to have to measure the power button. We're going to have to measure the DC input voltage, the 12 volts from the battery. We're going to have to somehow measure the current coming in from the 19 volts and add to that whatever else you want. We're going to have to use all of that in our circuitry. We're going to have to figure all that out and then feed it into some sort of logic circuit, right? So you can see it gets kind of complicated, but this is really important aspects of our power management circuits. Now, what if we want to turn it off? Well, the user generally will hold the button down, the power button down for longer to turn it off. So it's a short press to turn it on, but if it's on and you turn it on for longer, it will turn it off. So now we have to not only measure the power button is held down, but also have some timing to see if it's been held down for a long time and if the computer is already on. So if there's no battery voltage and suddenly the user unplugs the wall outlet adapter, then you want to turn it off. So you want to measure that. And you also want to turn it off if you sense an overcurrent on the 19 volt rail. So again, turning it on and off has got some requirements that we're going to have to not only measure, but also do some logic. Keep in mind that if the laptop is off and we want to press the power button to turn it on, we have to have a signal even though the computer is off. So we have to not only have a signal that says, hey, the power button was pressed, even though the computer is off, but also the logical circuit needs to be on to be able to recognize that the power button was pressed. If you plug 19 volts into the DC input jack, even though the computer's not on, you want to start charging the battery. So your power management circuit needs to sense that the DC input jack has good 19 volts so it can start charging the battery, even though you haven't turned the computer on. So behind the scenes, you've got to be doing some stuff. And also you have to supply power to the on button. So you can see power management gets to be kind of complicated. You've got to measure a lot of things. You have to have things in service even though the computer's off. So again, here is our laptop motherboard. We've got our adapter and our DC jack. So let's take a look at some of the ways that we can, once we plugged into this jack and we feed it into the circuitry, what kind of circuit can we expect in here to start doing some of those things we were just talking about? Well, we're going to have to turn the power on and off to the laptop, right? We mentioned that before. When we plug in or remove the DC from the input jack, we want to be able to switch that 19 volts going into the computer on or off based on those different considerations. So we want some controlled switches right after we plug into that input jack, right? But we want them to be controlled by some logic, and that's going to be called the power management integrated circuit or power management chip. And that is going to be doing a lot of the logic we've talked about previously, sensing whether it's okay to close or whether we should be opening those switches, right? But we need to have some controlled switches that take signals from the power management to open and close them as appropriate. So we're going to, for example, turn the power off if there's too much current flowing through this circuit, or turn the power on if the voltage at the input is okay. So we're going to have to measure those things if there's too much current in this circuit, and also making sure there's good voltage coming in. And then we can control these switches. So if we want to measure the current in this circuit to make sure there's no short circuits, and if there is a short circuit, if there's an overcurrent, we want to turn these switches off or open them if there's too much current. So how are we going to do that? Well, a very typical way in electronics, we talked about that in our ATX power supply for desktop motherboards. We talked about doing this very similar thing, and that is use a current sense resistor. What that is a very low ohms resistor in series with your main 19 volt, what's called a rail, and it might be like a 0.08 ohm resistance. But if you have 19 volts connected and you have, say, 3 amps coming in to feed your laptop, 3 amps times 0.08 ohms is about 0.2 or 0.3 volts across this resistor. So what you can do is you can measure the voltage across the resistor and feed it into your integrated circuit. And by knowing how much voltage, it can directly figure out, if it knows that this is a 0.08 ohm resistor, it can directly figure out how much current is flowing in that circuit. So if it's 0.24 volts across this resistor, we know that there's 3 amps through a 0.08 ohm resistor. So it's going to measure that, but you also need to tell the integrated circuit, hey, here is the value at which I want you to say, hey, there's too much current, open these switches. So you're also going to need some circuitry where you as a user tell this power management IC what's acceptable and what's an overcurrent that you need to open the switch. So basically we're going to take voltage in these 2 pins, and it's going to say, okay, if it exceeds the value that the user set, if it's over 0.2 volts, that means it's too much current, therefore I'm going to send a signal to these switches. So now what if we want this chip to determine whether it can close these switches and feed the 19 volts into our circuit? One requirement is we turn the power on if the 19 volts coming in from the power jack is there, right? If it's legitimate 19 volts, not too high, not too low, we can have this IC close these switches. However, we need to measure that. In the same way we need to measure this current sense resistor, we need to have some circuitry that measures the voltage coming in, feeds that to the power management IC, and it can say, okay, if it's around 19 volts, we're good, I can close this. Of course, there's other logic it can use, but that's the basics of how we can do that. So you can see not only we have the logic, but we also have some measurement circuits and some control circuits. Now, we've talked before in our series on electronics and our ATX power supply series what we can use to do these very simple controlled switches in electronics. We've got a control signal and then a switch. And the device that's used everywhere is called a Mosfet, metal oxide semiconductor field effect transistor. Basically all it is a switch controlled in one terminal by a signal fed to it by an external controller. And these are used in many different situations. We'll talk later how not only are they just on-off switches, but they can also be used in our circuits that will take the 19 volts and drop it down to 5 volts and 3 volts and 1 volt and so on. So they're very, very useful. So the MOSFET, basically we have a switch between the drain and the source, and the control terminal, the third terminal, is called the gate. And that's where you send a signal to either turn this on and off. You can send a high voltage or a negative voltage depending on the MOSFET, but you send it a signal and that will either turn the MOSFET on or off. So here is a very simple representation of the input circuit for your laptop, where you're measuring the voltage, you're measuring the current, and you're using those, among other things, to switch your input switches on and off to either apply or remove your 19 volts to your main power system, which will then take that and convert that to the lower voltages to feed the components. Now, one more thing about these MOSFETs. Here is a typical MOSFET, and it's got 8 pins. And the reason it's got so many pins, here we just show 3 pins, a gate, what's called a gate, a drain, and a source. But keep in mind, these MOSFETs can be carrying lots of current. Often for a laptop, it might be 3 to 5 amps. You can get more current, so you have parallel circuits tied together where you can have more current flowing. If you can have like 1 amp in one, 1 amp in the parallel one, 1 amp in the other parallel one, that allows you to carry 3 amps rather than just 1, so it gives you more current carrying capability. The gate doesn't need that because it's just a control signal, very low requirements. So this is typically what you will see for a single MOSFET in this configuration, where you've got a gate controlling it and then source and drain that are basically the switch to carry the big currents. So in the next videos in this series, we're going to talk about the battery circuit, where the battery can supply voltage to the motherboard and also it gets charged. And you can imagine it's very similar to this voltage source from the wall adapter, because basically you have to be able to shut on and off the battery like we did with the wall adapter. And we're also going to talk about a very interesting and very common circuit that turns out is used for basically all of these circuits that take the 19 volts and drop it down to the 1 volts or 5 volts or 3 volts or whatever we need for these components on the motherboard. It's basically one circuit that's reused in all these different situations. So it's really interesting. If you understand how this circuit works, you can understand a lot of what's going on in the motherboard. And we're also going to look at taking that circuit and making a simulation in what's called LT Spice, which is a free simulation software. I did a 13-part series on how you can simulate electronic circuits to really get a good understanding of how they work. You can measure values, you can look at gate signals, turning these switches on and off, and so on. So really great way to learn about these things and understand them on a deeper level. So that's it for this one. If you're liking these videos, I encourage you to hit the like button, subscribe, hit the bell notifications, but most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.